here's the center of the Earth, we'll say. So this is your distance right here because it's the center of the source and the thing that is being attracted to that source. So basically, nothing is moving right now, since you're not moving, there's not really a centripetal force because you're not in motion. But we do know that you have a certain weight on Earth, which is the same thing as the force of gravity. So Fg equals mg. But the force of gravity also is, this equation. Since both of these describe the gravitational force, or better known as weight, we can find the gravitational field by setting these equal to each other. And this is the thing that is being attracted to the Earth, which is you. And then when the masses cancel out, and then you get G equals G times mass of the Earth, or mass 2, over R squared. But remember, we do have to subtract 0.03 from our answer. And also, this is in feet. So basically the number of meters are in 29,029 feet is around 8,848.0392 meters. So that is the same as the height for math aberration, metric units. But remember that R is this plus the radius of the Earth. So that would be 6.38 times 10 to the 6 meters. So basically when you calculate G, you get around 10, not 10, 9.8, which seems pretty accurate, meters per second squared. But again, since there's a slight error, you have to subtract 0.03. And then you get G is equal to 9.77 meters per second squared on Mount Everest. So it does alter slightly, but when you go to higher heights, like even possibly like thousands of kilometers, this will change drastically. Because remember, the radius is squared, or the distance between them is squared. So, yeah. Another problem. So, a planet has 2.7 times the mass of the Earth, but the acceleration due to the gravity, which is little g, is the same as it is on Earth. By what factor is the radius of the planet compared to Earth? So basically, so m, so we're gonna have the weight equal to the gravitational force. So G m 1 m2 m1 over r squared. So G equals G m2 over r squared, and we'll call this r1. So this is kind of like the rule of thumb. G equals big G times mass of the source, and then over the distance squared. So these two planets have the same G, so you could basically set up a proportion. So so let's say G of Earth equals that, and then G of planet equals G m2 over r2 squared. But this planet has 2.7 times more mass of the Earth, so you multiply by 2.7. So we can set G equal to GP because they have the same acceleration due to gravity. So we get G m2 over r1 squared equals 2.7 G m2 over r2 squared. So the mass of the Earth cancels out, and same with the gravitational constant. So you get 1 over r1 squared equals 2.7 over r2 squared. So what we're trying to do is we're trying to find r2. So we're going to cross multiply. So you get r2 squared equals 2.7 times r1 squared. Then you square root both sides. You get r2 equals 2.7 r1 squared, all in the square root. But the thing is, you can actually take an r1 out because they'll just can't. The square root and the square cancel out, so you get that to equal to r1 rad 2.7. But the thing is, they didn't ask for the radius, they asked for the factor. So what we can do is, to find the factor, you could just divide by r1. And we see that they cancel out. So the radius of this other planet increases by a factor of the square root of 2.7.